Hello and welcome to lecture 40 of the course Theory of Computation. In the previous lecture, we saw what reductions are. We defined mapping reducibility, and then we saw we made two statements. One is that if A reduces to B, and if B is decidable, then A is decidable as well, right? So you could use the reduction from A to B and then the decider for B and combine them to get a decider for A. The other result that followed was that if A reduces to B and A is undecidable, then B is also undecidable, right? So that is what I have written over here. If A reduces to B and A is undecidable, then B is also undecidable. And this is going to be very useful for us. Right. So far, the main undecidable language that we have seen, that we have proved to be undecidable, was HALT-TM. Right. We proved from scratch using all the theory of countable and uncountable sets and all that. Right. So HALT-TM was the set of all Turing machines M and strings W, where M accepts W. In other words, we are asking, given a Turing machine M and a string W, we want to decide if M accepts W. Right. So now we are going to use the undecidability of HALT-TM and the fact that we can use the reductions, and using this theorem, we'll combine all this to show undecidability of other languages as well, right? So the first language that we will show undecidability is HALT-TM. So what is HALT-TM? Given a Turing machine M and a string W, we are asking whether this Turing machine M halts on W, meaning let M run on W. Does M halt on W or does M loop on W? Right? This is the question. And sometimes this is referred to as a real halting problem, right? Real halting problem, in the sense that HALT-TM also we sometimes refer to as a halting problem. But here is a problem where we are actually checking whether it is halting or not. So there is a reason why HALT-TM is also referred to as a halting problem, because the difficulty, so you can always run M on the string W, right? And this is, we can just report the output. But the challenge comes when M does not halt on W at all. So there is no way to tell whether it is going to halt or not. So the challenge is in finding whether M halts on W, even in HALT-TM. So that's why we sometimes refer to HALT-TM also as the halting problem, because the real difficulty there also lies in the issue of determining whether M halts on W, right? Anyway, the point, the statement that I want to say here is that HALT-TM is undecidable. So we'll see two approaches, or we'll see two ways to show this. Or they're essentially the same thing, but then we'll present it in two different ways, right? So there is a small thing that we are doing slightly differently from the textbook, CIPSR textbook. CIPSR textbook illustrates the notion of reductions using a lot of examples and lot of things, and towards the end of the chapter, CIPSR defines reductions. However, we have already defined reductions in the previous lecture, and now we are going to go through the examples. Right? Anyway, first, so here we will show that HALT-TM is undecidable. So first we will assume it is decidable and show that this implies that HALT-TM is decidable. And since this contradicts the known fact that HALT-TM is undecidable, this should imply that HALT-TM is undecidable. Right? This is the first approach. So let us see what the approach is. Okay. So suppose there is a decider for HALT-TM. Let us call it R. Right. So let R be the Turing machine that decides HALT-TM. Right. So this is a decider for HALT-TM. Let us call it R. So now let us see how we can use R to build a decider for HALT-TM. Right. So suppose we are given an instance of HALT-TM M comma W. We have to determine whether M accepts W or not. Right. We want a decider for this. So what we do is, first we run. We feed M and W to R. So R is a decider for HALT-TM. So this will tell, R is a decider for HALT-TM. So R should tell whether M comma W is a yes instance or a no instance of HALT-TM. In other words, R should tell whether M halts on W, yes or no, right? Suppose R rejects, then we reject, okay? And so what does it mean if R rejects? It means that it is a no instance of HALT-TM. In other words, M does not halt on W, right? So M does not halt on W, so then we reject. So maybe I'll just note it here. M does not halt on W. That's when we reject here. Suppose R accepts the pair M comma W. What does it mean? This means that it's a yes instance of HALT-TM, meaning M halts on W. But then halting could mean two possibilities further, right? M could accept or M could reject. So now it's easy because now we are assured that M halts on W. So then we just run M on W, right? We just simulate M on W. Now we just wait for the response because we know that it halts. So we just complete the computation, and if it accepts, we say yes and we accept. If it rejects, we say reject, right? So that is the decider for ATM, right? So given M comma W, basically we want to run M on W. This is what we discussed earlier in the last week. We can run M on W and output whatever we get. But the issue that we ran into was that what if M loops on W, right? That was the issue. So now that issue here is taken care by R. So R is a decider for HALT-TM. So we ask R whether M halts on W, and if R rejects, we know that M does not halt on W, and then if M does not halt, it does not accept. So then we can reject the instance. So we know that M does not accept W, so then we can reject. Even in ATM we can reject. If R accepts M comma W, which means M halts on W. So now we know M halts. So now we simply run M on W. So we accept if M accepts and reject if M rejects, right? So I've just written some table, the same thing that I've been explaining. If M accepts W, right, then R accepts MW. R accepts MW, right? And then we can say then we run. Then we run M on W. If M rejects W, even then it is halting on W, right? So in that case also the decider for HALT-TM R should accept M comma W. Again we run we run M on W in that case as well. The only issue is when M loops on W. So then we want to reject the pair M comma W. So now this is made easy by the decider for HALT-TM, that is R. So we run R on MW first, right? So R rejects. So then we reject, right? So then in this case also we reject. So these are the three cases: M accepts, rejects, and loops. In each of these three cases, we are able to determine what happens and then make a decision accordingly. This decider, the decider that we just built over here, this never loops, because if M loops on W, we never run M on W, right? In that case, we know because of R, right? So now the main component of this ATM decider is the HALT-TM decider, and by assumption the HALT-TM decider exists, right? So because we know that ATM is undecidable, in other words ATM decider does not exist, this should mean that HALT-TM decider should also not exist, hence HALT-TM is undecidable, right? So we cannot have a HALT-TM decider, hence it is undecidable, right? So that's the proof. So what we did here is to just build a decider for ATM from HALT-TM. So this is not a really like a reduction in the way we defined it in the previous lecture, right? Like a reduction was a mapping, and we from one instance we constructed from A instance we constructed B instance, etc. So here we are not doing that. We are just using HALT-TM to build a decider for ATM, right? So now we will see the same proof slightly differently, slightly different perspective. What we will do is we will reduce ATM to HALT-TM, right? So we said that if A reduces to B and A is undecidable, then B is undecidable. So what we will do is we will reduce ATM to HALT-TM. Since we know that ATM is undecidable, this implies HALT-TM is undecidable. So the idea of this reduction, I have already said it in this lecture as well as one of the previous lectures, right? So we need to reduce ATM to HALT-TM, right? So let's see what are the so ATM, let's say the instance is MW, right? So ATM, the instance is MW. And now what are the three possibilities? Either M accepts W, or M rejects W, or M loops on W, right? So M accepts W is the first instance that is written here, right? M accepts W. It is a yes instance for ATM because M accepts W. It's also a yes instance for HALT-TM, right? If MW was a HALT-TM, it's a yes instance. If M rejects W, right, it is a no instance for ATM, but a yes instance for HALT-TM, because HALT-TM is just checking whether it halts or not. So rejection is also halt. So it's a yes instance for HALT-TM, but a no instance for ATM. If M loops on W, it never halts, it never accepts, never rejects, it halts. It loops. If it loops on W, then it is a no instance for ATM. So because M does not accept. It's also a no instance for HALT-TM because it does not halt, right? So these are the three possibilities. So MW as an instance, if you feed it to ATM and HALT-TM, the outputs agree in the first case and the third case. The issue is with the second case. So if the same instance worked, then we need not do anything. Just the same M comma W could have been a reduction. But then we need to do something about the second case, right? This needs to be handled because it is a no instance for ATM, but it's a yes instance for HALT-TM, right? If we could do something, we could do some modification to the instance so that whenever M rejects W, we do not halt. It becomes a no instance for HALT-TM also. Then it will be fine. So the question is, can we modify the ATM instance MW so that whenever M rejects W, it does not halt, or we modify it into something so that the modified instance never halts. Right? So when M rejects W, we want to construct some M prime W prime such that whenever M rejects W, M prime loops on W prime, right? So in fact, what we will do is we will not construct a separate W prime, we will have the same W, but we will construct a different M. So we will construct M prime. So what M prime will do is it will follow M mostly, but instead whenever M has to reject, M prime goes into a loop, right? So what we can, this is not that difficult to accomplish. I will not written in detail, but so Q reject in M we replace by some looping state, Q loop in M prime. So Q loop can be a loop state, meaning once you reach Q loop, you just get stuck there. The transition just keeps you in Q loop and never go out, right? So if we make this modification to M, right? Now whenever M was supposed to reject a string, M prime will now just start looping, right? So that's what we want, and that's what I've written here. M prime, this is the main idea of M prime. Whenever M rejects an input, M prime we want it to enter into an infinite loop, right? So basically whenever M rejects, right, that was the issue here, right? This second line here, whenever M rejected W, it's a no instance for ATM. The HALT-TM instance, we also want to do a no instance for HALT-TM. So we make it not halt, we make it loop. So the reduction machine will just output M prime and W. Right? So we know how to construct M prime. It's just a simple modification. When you replace a Q reject in M with a Q loop in M prime, so where it just loops. Right? So that is the reduction process. So the construction of M prime. So this is a very small modification, we can easily do it, and it's not that difficult to see now. So now the no instance of ATM corresponds to a no instance of HALT-TM also, because the M comma W is a no instance of ATM, M rejects W. The map instance is M prime W. So M prime loops on W whenever M rejects W. Whenever M accepts W, M prime also accepts W. Whenever M loops on W, also M prime loops on W. So that there is no change in the first and second, the first and last situations. The difference only is only in the second case when M rejects an input, and that is now handled. So this means that whenever M comma W is a yes instance of ATM, if and only if M prime comma W is a yes instance of HALT-TM. Right? So this shows that, just to write, so maybe we'll use a different color, red color. This indicates, right, this indicates that ATM reduces to HALT-TM. This means, I don't think I wrote it anywhere. This means that HALT-TM is undecidable. That's what we said at the beginning. If A reduces to B, A is undecidable, then B is undecidable. Right? So that's how we show that HALT-TM is undecidable. So first we saw the sort of a direct approach where we use the HALT-TM decider to construct an ATM decider. Now here we are actually presenting a reduction from ATM to HALT-TM, where we modify the ATM instance to construct a HALT-TM instance so that it's a proper reduction. Yes instance map to yes instance, and no instance maps to no instance. Right. Now some more languages using Turing machines which we will show to be undecidable. Right. So the first language is ETM. ETM, given a TM, we are asking whether this recognizes the empty language. Right. Given a TM M, we are asking whether this recognizes the empty language. Right. So this is also undecidable. So let's say why. So we will reduce ATM to ETM here. Right. So given an ATM instance which is MW, right, we will construct an ETM instance M subscript W. Right. So this is ATM instance. Will construct ETM instance. So M comma W and M subscript W means it's a Turing machine alone. There is no string because ETM instance has only one Turing machine, but we'll use W will be important in the construction of M subscript W, right? So what does MW do? So whenever M accepts W, we want MW to be so in fact we'll see what the reduction is, and then I will talk about this, right? So MW is this. Whenever there is an input X to MW, so X is the input to MW, okay? X is the input to MW. If X, so now MW knows W, right? So W is like a fixed string that it is aware of. If X is the same, if X is not W, it rejects, right? So it first checks whether X is equal to W. If X is not equal to W, it rejects. Okay, so that is the first step that MW does. So it rejects for any input that is not W. Right. So the only string that it may accept is W. So let's see what it does when the input is W. If the input is W, it runs M on W and then does whatever M does. Right. So M may not be a decider, MW may also not be a decider, right? So if the input to MW is not W, it rejects. If the input to MW is W, we run M on the input W, right, and we do whatever M does. If M accepts, we accept, V meaning MW. If M accepts, MW accepts. If M rejects, MW rejects. If it loops, MW also loops, right. So of course this loops means it just loops, there is no reporting, right. So let's see what is happening here. Suppose M accepts, so there are many inputs, right. There are many possible inputs that many strings are possible for as inputs for MW, right. So it rejects all of these inputs. The only string that it even considers is the string W, right. If the input is W, then it checks whether does M accept W, or does it runs M on W, right. Run M on W and do whatever M does. Okay. So it rejects everything that is not W and then runs M on W if the input is W. So if M accepts W, then MW also accepts W, right. If M accepts W, right, then MW accepts W. If M rejects W, right, then MW rejects everything that is not W. That is always the case. If M rejects W, then MW also rejects W, which means MW does not accept anything. If M loops on W, even then MW does not accept W. Even then MW does not accept any string in the alphabet, right, over the alphabet, because all the strings that are not W is immediately rejected. The only string that it has any chance of accepting is W. So if M rejects or loops on W, then MW also does not accept W, right, which means that if M does not accept W, MW does not accept any string. So the only possibility that MW accepts some string is if M accepts W, right. So that's what I have written here, right. M accepts W means the language recognized by MW is not empty. So the language recognized by MW is just, there are only two possibilities, either it is empty or it is a single string W. If M accepts W, LMW is the single string W, right. If M does not accept W, LMW is empty, right. So M accepts W if and only if L of MW is not empty, right. In other words, we are saying that M accepts W means MW is in ATM, and LMW not empty means that MW is in the complement of ETM, right. It is not an empty language. So what we have here is a reduction from ATM to the complement of ETM. So ETM asks whether the given Turing machine recognizes the empty language. This is the ETM complement, means it's the given Turing machine recognizes something which is non-empty, right. So ATM reduces to ETM complement. This means that ETM complement is undecidable. This means that ETM complement is undecidable, right, by our theorem that I stated at the beginning of the lecture. So this means that ETM complement is undecidable, and if some language L complement is undecidable, then L is also undecidable, because if I had a decider for L, I could just run the decider for L and flip the accept reject states to get a decider for L complement. So this implies that ETM is also undecidable, right. So the trick here was to create a Turing machine that only accepts W. So if and only possibly accepts W. So whenever M rejects or loops on W, MW does not accept anything and the language is empty. Whenever M accepts W, the language is not empty. right? So that's the proof here. There is one other language, EQTM. So EQTM is given two Turing machines. We are asking whether they recognize the same language, right? Just like EQDFA or EQCFG, right? This is also undecidable. There is a very straightforward reduction from ETM to EQTM, right? So it's similar. So basically, we construct a Turing machine that rejects every string. We construct a Turing machine that rejects every string. So to determine whether a given Turing machine recognizes the empty language, we can ask whether this Turing machine is equivalent to the constructed Turing machine, which also recognizes the empty language, right? So I don't want to get into the details. It's very straightforward, and it's on the similar lines to other proofs that we have seen. So I suggest to read the proof from the book. Okay. The next language is regular TM. So what is regular TM? Regular TM is given a Turing machine, we are asking whether the language recognized by this Turing machine is a regular language. Given a Turing machine, we are asking, is the language recognized by this Turing machine a regular language, right? So this is also undecidable. Again, we show it by reducing it from ATM. So we reduce ATM to regular TM, and this implies that regular TM is undecidable. So let's see how to construct the reduction, right? So given an ATM instance, we'll show how to construct a regular TM instance. So notice that regular TM instance is just one description of a Turing machine, right? So given an instance m comma w, which is an ATM instance, we'll construct a Turing machine m prime, right? So this will be the regular TM instance. M prime will be the regular TM instance. Okay, let's see what it does. M prime, when it gets an input x, right? So x is the input of m prime, right? What it does is it first checks whether x has the form 0 power n, 1 power n. Notice 0 power n, 1 power n, where I want the number of zeros and the number of ones to be the same. So both have the same repetition. Both should appear n times. So if the input x is of this form, we accept. Nothing else needs to be checked. If it is not of this form, right? So suppose it's some other string, let's say 0 1 1 0, something like that, right? Or something 1 0 1, some other form. Then what we do is we run m on w. Okay, we run m on w. Okay, so where m and w are as in the ATM instance. So m prime actually depends on m and w, right? M prime knows what is m, knows what is w. Then we run m on w. Again, it is not x but w. So we run m on w, and if m accepts w, we accept x. If m accepts w, m prime accepts x. Okay. Let me repeat what m prime does. Given the input x, it checks whether the input is of the form 0 power n, 1 power n. If it is of that form, it accepts. If it is not of this form, it checks whether m accepts w by running m on w. It accepts x only when m accepts w, right? So it runs m on w and it accepts x if m accepts w. So let's see both cases. Suppose m accepts w, right? Suppose this always happens. Suppose m accepts w. Now all the strings that are of 0 power n, 1 power n form are accepted. If x does not have this form, right, we run m on w and accept x is m accepts x. Sorry, m accepts w. If m accepts w, we accept x. So if m accepts w, we accept x, which means that all x is accepted. If x is not of x is of this form, we 0 power n, 1 power n, we anyway accept. Otherwise, we accept over here. but in short, all x's are accepted. In other words, the language recognized by the Turing machine M prime is sigma star. It accepts all the possible strings. If M does not accept W, right? If M does not accept W, right? So then here it does not accept W, which means here we do not accept X, which means if X does not have the requisite form, meaning if X is not of the form 0 power n 1 power n, it is not accepted. So the only X that is going to be accepted are through this line. Right? The only X that are going to be accepted are going to be through this line, 0 power n 1 power n. Right? So if M does not accept W, the only X that is going to be accepted are 0 power n 1 power n, which means the language recognized by the Turing machine M prime is just the set of all strings of the form 0 power n 1 power n. I will just repeat this because it's kind of the key part here. If X is of the form 0 power n 1 power n and you accept, if X is not of this form, we run M on W and accept X if M accepts W. If M accepts W, this means that strings both of the form 0 power n 1 power n and not of the form are also accepted. So which means every string is accepted. So the language recognized by M prime is sigma star. If M does not accept W, then strings not of the form 0 power n 1 power n are not accepted. So the only strings accepted are 0 power n 1 power n. Right? So, but now let us see what these languages are. If M accepts W, then the language sigma star is a regular language. Right? Sigma star you can easily make it's almost like a regular expression. Right? If M does not accept W, then the language is one of our favorite non-regular languages, right? 0 power n 1 power n. So which means M accepts W means that M prime the language recognized by M prime is regular. M does not accept W means the language recognized by M prime is not regular. So the language recognized by M prime is regular if and only if M accepts W, right? So in other words, M comma W is an instance of HALT-TM, meaning if and only if L of M prime is regular. And L of M prime is regular if and only if M prime is in regular TM, right? By definition of regular TM. So M comma W is in HALT-TM if and only if M prime is in regular TM, which means now we have a reduction from HALT-TM to regular TM. Mapping reduction from HALT-TM to regular TM, and also the construction of M prime is something that is computable, right? So M prime, we just have to encode these simple things. If X has of this form, we should accept. If it does not have this form, we know M and W, we just run M on W. That's it. So the construction of M prime is computable, and also we have this this correspondence M comma W is in HALT-TM if and only if M prime is in regular TM. So the key thing again is that M accepts W if and only if L of M prime is regular, right? That's the key thing. So M accepts W, which is this, if and only if L of M prime is regular, which is this. Hence regular TM is also undecidable. Right? Regular TM is asking, given a Turing machine, asking whether the language recognizes regular. So I just want to quickly tell two things. So regular TM is asking, given a Turing machine, is the language recognized by the Turing machine regular? ETM is asking, given a Turing machine, is the language recognized by the Turing machine the empty language, right? So in both these cases, in both these cases, regular TM as well as ETM, we were given a Turing machine and we were asked, is the language recognized by this Turing machine, does the language recognized by this Turing machine have this property? In one case the property was that is this regular, the second in the second case this property was that is the language empty, right? So So both had that structure, and we showed that it is undecidable. So in fact, it turns out that we can generalize this. So the statement is called, this theorem is called Rice's theorem. So the point is this: if so, consider a language called property TM. So property TM is like, given a Turing machine, we are asking whether the language recognized by the Turing machine, so that's important. The language recognized by the Turing machine, does it have some property? We are not asking whether the Turing machine has some property, we are asking the language has some property. Like, is the language regular? Is the language context free? Does the language have at least 1 0? Is the language, is all the strings in the language palindromes, right? So all these are questions of the language. So we are asking, does the given Turing machines, for the given Turing machine, does the language recognized by this Turing machine, does it satisfy a specific property, right? So that is property TM, right? Rice's theorem states that whatever be the property, or if the property is interesting or not trivial, this question is undecidable. So we already saw that regular TM is undecidable. We already saw that ETM is undecidable. So regular TM is asking, does the given Turing machine recognize a regular language? ETM is asking, does the given Turing machine recognize the empty language? So whatever may be the property that we are looking for, the testing of whether this Turing machine recognizes a language with this property, for any specific property, the answer is undecidable. It's not decidable. So that we will see in the next lecture, and that's it for me in lecture number 40. We just use the statement that if A reduces to B and A is undecidable to show that B is undecidable. We first showed HALT-TM is undecidable, then we showed ETM is undecidable, then I briefly discussed EQTM and asked you to read the proof, and finally we saw regular TM is undecidable, right? And in the next lecture, lecture number 41, we will see Rice's theorem, where we will see that for a given Turing machine, testing whether this Turing machine, the language recognized by this Turing machine has a certain property. This is also undecidable for any property, right? So see you in lecture 41. Thank you.